data stream can never be stopped. So things like delayed data arrival and things like out of sequence messages, how do you deal with it? So the stream layer doesn't have a luxury of doing accurate calculations because the data is full. Uh, in Lambda architecture, the advice is you either ignore such edge conditions in your stream layer, or you do an approximation and proceed, right? Whereas at the end of the day, when you run the batch layer, you make those corrections. Okay, because late arrival data and all those things will now be inside the batch layer, and you can pick up those erroneous messages that you had quarantined in your stream layer, and you may try to correct it. Druid works on the same concept. If you look at the Druid architecture, you have these four different nodes responsible for different things. So we have this batch layer, which is basically a historical nodes, right? Whereas we have a real-time node, which kind of handles your streaming data. It kind of indexes as the data gets in. And then we have a query node, which is, we call it a broker. It takes the queries and accordingly divert the queries into either real-time or historic, as may be the case, right? For example, your query boundary is from now to last 1 hour, and you have a logic of pushing your data after every 15 minutes to historic node. So last 45 minutes data will come from historic, whereas the current 15 minutes will come from the real time. And then there is, of course, a monitoring, and Druid depends on Zookeeper for monitoring, right? That's the Druid technology. The beauty of this technology is, if you look at the Druid data model, everything is revolves around the time. So that is your first partitioning condition. Druid call it as segment. And then onwards, there can be other dimensions with which you want to kind of segment your data. But the first dimension in which you have to kind of segment your data has to be the time. And you can define your rollups at different level. You can do it at the ingestion time. You can define the rollups at the query time, and so on and so forth. And these are written in JSONs. So Druid queries are written in JSONs. In fact, the ingestion instruction set specs are also written in JSONs. So we talked about processing technologies. We talked about processing technologies covers Spark Streaming, Flink, Druid, right? We talked about the pipeline, the producing technologies like Kafka. Let's talk about some storage technologies. And I think I only have Cassandra. The Cassandra as a storage is an excellent time series storage. The reason is the architecture of Cassandra is very simple, right? You have, in this case, you have 6 machines, 6 computers connected with one another. The beauty of this architecture, it's a peer-to-peer architecture. There is no master or no slave, right? Every machine is given equal importance. So there is no concept that my master goes down, my entire cluster goes down, so I have to fall back upon a secondary master. There is no concept like that. It's a highly fault tolerant system because each node talks to each other using something called gossip. So internode heartbeat exchange, whether every node is up and healthy, every other node knows about it, right? There are some advanced concepts like virtual nodes, which means that though you have 6 nodes here and you should ideally partition your data into 6 partitions, uh, what Cassandra does is there is a logical way of partitioning which is different from the physical nodes. So the logical way of partitioning might be 256 logical or virtual nodes on top of these 6 nodes. It just helps in better distribution in case one node goes out. Okay, so logic virtual nodes is a better approach than actually doing it in a physical distribution. And there are some advanced concepts like snitch. You can have it in multiple geographies. You can make it a cluster aware configuration and all those topologies. There are concepts of hinted handoff where, okay, one node goes off, and there's a beautiful analogy, right? So what happens when you go out for a vacation? When you go out for vacation, you tell your neighbor to hold your mail till you come back, right? So similar thing happens in Cassandra. So you, with hinted handoff, okay, you can expect a node to keep your data, okay, till the other node, till that node comes back online, right? So Cassandra has various advanced techniques to do fault tolerance. This is an important concept in order to understand Cassandra. So let me talk about this one. Okay. So if you look at your table, right? You have in Cassandra table, you have very important thing called a partition key. So what this partition key tells you is in which node the data should go. So 73 goes to this node, right? 44 goes to this node, and so on and so forth. I don't know if you can see my pointer, but basic concept is uh, the partition key determines which node your data lands. Then let me quickly check. There is a message. All participants are requested to mark their attendance. Okay. Um, so the rest of the columns in Cassandra, they can be stored, but among rest of the columns, for every partitioning key, there is a concept of uh, what do you call it? Clustering keys, right? So if you look at a Cassandra table, I have an example of Cassandra table later. The way you create it is you first tell what is your partitioning key. That means you're telling where in which node the data should go, right? The second thing you have to tell is what is your clustering key. So inside that node, how your data should be arranged. So if your clustering key in this case I see is address, and probably then there is a quantity and then or city and then state. So that's how the data are arranged one after another. Okay, uh, and why Cassandra forms an excellent time series database is because you can use this notion of clustering your time series window one after another. Okay, you can tell my sensor ID 1 goes to node 1, sensor ID 2 goes to node 2, but once you're within that node, the clustering concepts keeps your time. You can use your timing windows as your clustering keys, right? And inside each of these clustering keys, the data is stored in a key value format. So that is the reason Cassandra is considered one of the best storage technologies for time series as far as NoSQL is concerned. And not to mention, right, the kind of low latency that you get in NoSQLs, you can never expect it from ANFS or normal file systems, right? Okay, so we have arrived to the last part of our session, and we are I think we are on time. We have covered 1 hour. So in next 20 minutes, we're going to take you through one of the use case, okay? And so let me explain that use case first, and then let me hand over to Roshni and Aditya to demonstrate that. Okay, let's step back, right? We have done a lot of things today, okay? And what we have done in fact, so we have seen how the sources are there. These can be different IoT sources, but at the end of the day, the nature of these sources are very high velocity data, unbounded stream of data, and small payloads. So these are not huge like gigs of information, right? I mean, each payload at every point of recording can be in bytes, right? Like what is the milliwatt usage of that smart meter, right? Next, there is a concept of producer, which kind of collects the data from multiple places, serializes and generates a stream of data. It's kind of federating agent, right? And then you push it to a pipeline. And the responsibility of this pipeline is partitioning and sharding and parallelizing. It has to be a very fault tolerant pipeline, and it has to be highly scalable. Whenever required, the number of pipeline increases. Whenever not required, it goes down. So horizontal scaling has to be there within this pipeline. And that goes with the idea of sharding, right? The fourth piece is the most important piece, where we talked about different windowing functions, aggregators, transformations, cleansing, all these kind of transformation on the streaming data can happen. And think this in junction with Lambda architecture concept, right? You don't have a luxury of doing all the processing in your stream path. You may have to ignore some of those data points which are outliers. You may have to do approximation of those data points at some cases. But if you implement a Lambda architecture, some of the problems that you get in your stream processors can be taken care by a batch processor later at the end of the day. And lastly, on the consumption side, you can have two kinds of consumption: a typical BI kind of consumption, which you see at the end of 4 hours or at the end of the day, which are typically stored in disks. And disk storage is high cost because you have to actually write to a certain sector of the disk. Cassandra does it very good. So if you have a need of low latency storage, go for NoSQLs, or you may keep it in memory for real-time insights, or you can generate an alert or send a notification to some system if it is a immediate real-time insight you want to pull out from this pipeline. Now, this is the architecture or the pipeline for the demo that we had built, and we use this smart meter use case, right? So we had customers data, smart meter data, and these are the number of rows, how many data were there. And an interesting use case that we did is kind of cross-stream joins with smart meter data along with the weather data, because we've seen energy usage has a high correlation with the weather, right? Heaters, dryers, air conditions, all of these usage pattern changes. And some of the complexities, I'll just name a few. For example, your weather information and the smart meter information, these are cross-stream joins. It's very difficult to join, okay? The reason is the dimensions of each of these streaming pipelines are different. Weather may be collected at a district level, okay? Or maybe at a locality level, neighborhood level. And the smart meters, latitude, longitude, can resolve it in some other dimensions, right? I mean, weather can be, in that smart meter dimension, district may not be one of the figures. It can be something else, like city, zip, and state. So how do I do those cross-stream joins? Those becomes a very challenging situation. But anyway, we used Kafka to get this data, okay? And then we did some data preparation, validation, file completeness, all those kind of thing, cleansing, and did some date transformation, geotagging. And then...
Hi, Mike. Hi, Ryan. Good morning.
Okay, and then we used Flink for doing the data transformation and preparation. You can see these other two technologies. We also used Spark Core and Spark Streaming, but I mean, we are not going to show these in our demo today. But we did this to compare with the Flink performance, and then we took it into Cassandra, and then we used some of the consumption technologies, BI tools, to analyze the data that we got.
I haven't seen any new updates, even from the Ruby team.
Hi.
Last I saw where they had asked for credentials to the FTP. They wanted to have a look.
Okay. Thanks for going on mute. Okay. Let me pull back the presentation once again. Sorry for the interruption. Can you see my presentation? I will take a look at my chat window.
Yes, we can see Arrow.
Great. Okay. So we were talking about this pipeline, and I want to overlay the different bubbles that I showed you in the previous slides, right? We are talking about the produce sources, then we talked about the pipeline, and we talked about producing this, because the way in the POC that we had done, we didn't have the smart meter installed in different homes. We got the data dump and we got it in the files, CSV files, and we created streams of data per line reading that file, right? So we have a Kafka queue, and then we used Flink as a consumer/processor of that pipeline, and then for target we used Cassandra. So let me explain you this use case. So this particular use case is what is the present load? Every word is very important, right? What is the present load for the utility company? I want to analyze that. So the requirement goes like this: like, as a utility company, I'd like to know the total energy usage by locality. So there is a drill down on certain geographical factors, right? Country, state, zip, house. So there's a concept of house ID and household ID. House ID means the building, right? And inside the building, there can be multiple families staying, and those families are household ID. And I want to see it over last X hours, and this X can be predefined, like 6 hours, 12 hours, 18 or 24, or it can be generated on fly. This dashboard should go back 24 hours, and then the data point granularity should be in minutes. There should be some filtering conditions and so on and so forth. So if you looked at the UI that we are talking about some fine-grained data, where we are talking about cities, right? So the requirement states that at whatever granularity level you are in, okay, you have to not only show that level, for example, city, but you also have to go a level higher and show a baseline for the state, right? So if you are in say state level, you have to show the baseline for country, and so on and so forth. So that's how the expect output is expected. I'm hearing some bips. Let me quickly see if we are recording it. Okay, okay. Uh, Sorry. So I will not go into details of these, but these are different steps of Cassandra modeling. I had a different session for doing Cassandra, but the entire slide, if I have to sum up in one line, I must say that the way we model Cassandra is all by consumptions, and we have different queries for each of these workflow. So we determine an application workflow, how the user is going to address this use case one, and prepare different queries for every stages. Okay. So I will not go into details, but basically, again, for filterings, we had a set of tables. For doing the sort by, we had a different tables. For doing fine-grained data, because you remember the fine-grained data is from the household ID. So even for the detail level data, that's cities, we have to do an aggregation. For the baseline, we have to do another level of aggregation. And that's how we designed these tables. So these are my different tables. We got it by different geographical level. You see, the country is my, in this table, the country is my partition key. That means individual country goes to individual node. Whereas in the second table, the state is my partition key. K means the partition key. And that means the different state goes to different nodes. So these are two separate tables. And likewise, we have 6 such tables. And then we figured out this is a very bad design. So we went ahead and said, let's have something called location primary level, secondary level. And we had a notion of defining these levels. So I don't know. Yeah, here. So we have a location level, and we said, well, let's kind of enum it and say what each of these level mean and try to store it in every detail. So I don't have the time to explain you the individual storage way, but just take a look. I mean, typically in a one day session, I go and explain every update from this record. Each of these have significance, each of these values. But at the let me tell you that the way I have done it is like every minute, right? So these are my contiguous tumbling windows for a particular zip code. For another zip code, I have another series of tumbling windows, and so on and so forth. Cassandra has a concept of TTL, time to live, so that after a certain period of time, you can want to purge your data, you can get your data evicted, right? So anyway, this is the kind of visualization we got for two different, the state and city. Yeah. These are some of the observations from a performance standpoint we have seen. We have done batch and streaming. These are the millions of records we handled. These times are not very promising, I know. Even these are in billions. These are not very in millions, sorry, not very promising. The reason is we were using a very low end machine. Okay, forget about cluster. In some cases we used cluster for 3 nodes. In some cases we used, for most of the cases we went for 1 node, and these are not powerful machines. And here's a glimpse of how the dashboard would look like from a Flink aspect. It will give you different times. This is my table structure, and so on and so forth. So here is a set of observations which I mostly talked through while explaining these use cases. We talked about TTL, we talked about white column family of Cassandra. Okay, so Cassandra cannot do good server-side calculation. I mean, if you have a very complex calculation you want to do at the query layer and let Cassandra do all those calculation, it cannot be done. Basically, you have to kind of prepare your data, cook your data, aggregate your data before you put it in Cassandra. And there are other observations as well, which you can go through. I think I talked about most of the important ones. So Roshni, yeah, so I promised you 20 minutes, but I have 10 minutes now. Can we go through the demo while I take a note of the questions that were there in the chat window?
Yeah, sure.
So I will unshare my screen. Yeah.
Okay.
Okay, so Roshni, go ahead with the screen and let me go through the questions. I'll go on mute.
Yeah. Hello everyone. Is my screen visible now?
Yes.
Okay.
Yeah, that's me. Yeah.
Okay. So now I think everyone would have got some glimpse about how streaming technology works. So as Oro explained, we have implemented the use case using the metadata. So I'll just quickly walk through like what code we have written, and I'll just run one time to show you guys like how the Flink program can be run. So this is my data. This is a sample data. So just to explain you people, I have just copied few of the sample records from my file and to explain it over here. So in my file, I'll be having like ID and timestamp, which is basically will be in epoch Unix epoch timestamp, and this is the value on which we are going to perform certain kind of aggregations. And there is something called as property, which is like not much relevant over here, and we have some columns like plug id and household id and the house id. So basically in the use case what we are going to show is for the particular house id, for a particular time, like what is the energy consumption. So this value is nothing but our consumption of the energy for that particular house id. So this is about the data. Whatever the stuffs we have implemented, so everything now we have deployed in AWS machine. So whatever things I am going to show over here will be in AWS. So this is like our own account wherein we are running our code. So whatever the codes is implemented, it's there in the Docker. So whatever the Flink technology, streaming technologies and NoSQL database we are using, we are actually using the Docker images.
Hey, sorry, I think Roshni will have to rejoin once again. So while Roshni rejoins, guys, you can put your questions and I can try to answer those.
Hello?
Yeah.
Am I audible now? Yeah, okay. Sorry.
So Roshni, now you can share your screen, please.
Yeah.
Thank you.
Is it visible now?
Yeah.
Yes. It
Uh,
is.
yeah. Sorry, it got disconnected. So yeah, I was talking about the Docker images which we used for the complete use case implementation. So here you can see like multiple Docker images are running. Like we have used Flink, and we are using Kafka for the streaming data to ingest the data onto Flink, and we have like Cassandra database running, and we have Redash, which is data visualization. So one by one, I'll be showing like how we have implemented and what is the like process to run our job. Okay, so this is a Docker images. I spoke about the data already. So whatever the data you are going to process from the Flink, that should reside under your Flink Docker, and this is the directory wherein your data should reside. So I am into Flink Docker, and this is the place where my data resides, on which I will be going to perform my streaming operations. So this is my file, sample file on which I'll be running my job. So this is about the data. The second thing is the Cassandra table, which we have created, on which the data will get loaded onto. So this is my table. So this is the structure of the table which we have created. As Oro showed in one of his slides, like we are using something called as level, and then there are like some fields like primary location, secondary location, and what is the timestamp, and what is the energy consumption in that particular timestamp for the house ID. Okay, so this is my table, and these are the keys which we have used to create this table. So let me quickly run through you all the code. So this is my Kafka Flink producer. So my first step is to read the data from the file which is there into your Flink machine. That data will be ingested using Kafka. So this is my Kafka producer code. So this is the topic which I'll be using to ingest my data. So this is my this actually whatever values you can see in palms.get, all are like all can be like overwritten. So future, if you want to run with some different topic name, you can actually override it from the UI. Okay, so this is my Kafka producer code. So this is like API which we are using, Flink Kafka producer. This one I'll not go into the detail of this. So this is the producer code which will be actually producing the data. Okay, and these are like my Kafka configurations. The second job is Flink job, which actually process the ingested data from the Kafka. So this is like my certain basic configuration which we have to write before starting the processing part. So this is like my environment creation, which will actually create the streaming environment. So once the streaming environment is created, you have to read the data. So once you come to this method, so here actually show like what and all operations we are performing, like filtering, and this is like all depends on your use case. Okay, the next part is, so this is like my processing part. So once you go to this enriched part, okay, so this enriched part is like the main function which we are using to enrich our data. Like whatever data we are getting from the Kafka, we are performing certain kind of like transformations. Okay, so this create enrich function is there. As I explained, like we are using from some filter function, and we are using some like map function and all. Okay, so this is the processing part, this step. The third step is like, once the data is processed, you need to write it into Cassandra database. So if you go to this create Cassandra sync, so this will actually tell you like what all configurations we have used to create the Cassandra database. Okay, this is my host name, and this is like my port ID on which my Cassandra database would be running in. So this is like a default port ID where Cassandra runs. Okay, so if you have actually set up this Cassandra in some another host, there also the default port would be like 9042. But again, these things are like changeable by the user. Okay, so this is the stuff. And yeah, so this is like actual writing it into Cassandra database. So as Oro explained some of the windowing functions, so actually we are using event timestamp. So what type of processing you have to use, you need to declare it. Okay, so that one we have already declared it. Like we are in this case we are actually using event time. So once it is specified, like we have to use the event time, so based on that the data will be processed. Okay, so this is like my this is like my writing the data onto my Cassandra database. So in this particular uh, part, you need to specify like what is my table name on which I have to write my data. So again, this parameter is also like overwritten, can be overwritten by the user. So okay, and this is like my Cassandra configurations. So I'll quickly like execute. Yeah. How should I remove this? Okay. Yeah. So this is like my Flink UI. So once my code is ready and the jar is created, I just uploaded my jar onto this UI. So this is like the Flink will be running it into 8081, which is like a default port ID for the Flink, and this is my host ID on which my Flink job is running. So this is like AWS environment. So here first I would be running Kafka Flink producer, giving the topic name which I want to use. Okay, so on this particular topic, my data would be writing from the Kafka. So once I'll execute this, the second part will be like executing the Flink processing part. So this is like my code which I would be using it over here, and these are like my configurations which I would be overriding. Okay, so let me quickly submit the producer part. So now my producer is running. You can see it over here. Okay, so here you can see like what's the parallelism, and what is the status of my job, like how many records have been received and all the stuffs you can see. Okay, so and this one, now let me quickly submit my consumption, the Flink job. Okay, yeah, so now this is also running. Now let me show that particular table. So this is my table on which the data would be writing. It started writing. If you can see, these are like continuous running jobs. It will keep on running. If you see here, it will keep on increasing as it is a streaming data. Okay, so now by this way, actually now your data is ingested into your Cassandra table. So once the data is there in the Cassandra table, you can actually visualize this data from Redash. So here we have used a visualization tool called as Redash, which has a default Cassandra connector. By using that default Cassandra connector, you can actually create your queries. So I have like executed one query. Right now I'm not running it again. So I have ran it before the demo. So this is like my query which I executed on the same table. So here also you can actually see in a proper structured format. Okay, and based on this, you can actually create the visualization. So I have created one visualization over here. Okay, so this is not exactly like the use case which Aura was explaining, but this is like a real-time stuff which I want you guys to see. So this is like a visualization which is created based on this particular table data. Okay, so based on that data which you have, which the visualization you have created, you can see it in the dashboard also. So this Redash is basically a visualization tool. If someone is not comfortable with like CQLSH command line stuff, so they can come over here and they can visualize their data. So it's all like user depends on the use case, like what and all filtration they have to apply and what and all stuffs they have to do, they can do it. So this is like a small demo. Any questions?
Yeah, thanks, Roshni. Yeah, so let us open for questions. It's last
Okay.
10 minutes.
Mm-hmm.
So yeah, I was answering some of the questions over chat, but if you have any questions, go ahead. I'll try to answer. And yeah, Adi, you can also participate.
Okay. I can see few questions. Um,
Yes, most of the questions are taken care from the chat.
okay.
Yeah. So guys, if you want to speak up and ask any question, you're welcome to do so. And the chat questions, we are anyway keeping a history of these. We may get back to you through your email. Uh,
Hello.
yes, go ahead.
Hi, Arvind. This is Jagdish here.
Hi,
So I have
Jagdish.
already posted my question in window, but I will ask it. So
Okay.
in Storm, whatever data, streaming data we are getting,
Hmm.
we can parallelly process in different functionality to the same stream data
Okay.
simultaneously. But
Yes,
is there any way it is possible in Flink?
it is. Flink is highly parallelized. I do not have a slide to compare Storm versus Flink, but to answer your question, yes, Flink can be highly parallelized. It can run on parallel machines.
No, no, no. That is anyway is possible. I know.
Hmm.
So my question is, say for example, if I am getting uh, 2 comma 2, okay, as a input stream.
Okay.
Now I want in one process I want to add them. In another process I want to subtract them. In
Yeah.
another process I want to multiply them. So
Yeah.
all these can be done in parallel.
Absolutely. Yes, it can be.
So
If you
different functionality can be done.
Yes,
Okay.
if you remember when I was explaining the windowing function,
Hmm.
okay, some of the windowing functions such as the sliding window is
Hmm.
basically a parallel operation for individual sensors, right? Yes, you can do it. To answer your question, you can have different operators running independently of one another in parallel.
Okay. So is there only way doing using windowing?
No, no, windowing is one of the many use cases of streaming data. So
Hmm.
today we just focused on the windowing. If you just the example that we gave, right? Forget
Yeah.
about windowing.